By the end of chapter 7, we are going to give a summary about the most important ideas we studied. But before, we are going to move to page 112 and read. Did you know differential calculus is an important part of A-level mathematics and is widely used in many branches of science, engineering, and business. So, differential calculus is not only used in mathematics, there are many other practical use for this part, as we already studied earlier, may be used in physics, engineering, and many other branches. Understanding it will help you to sketch a function by finding the maximum and the minimum values. So, studying differential calculus can help us sketch curves and find the values easier. Differentiation enables us to find the exact value where the volume of the box described in chapter 4 is maximized. So it's very important for us to focus on this part of mathematics so we can apply it in other sections of science. Let's go now to page 132 and look at the summary. The gradient of a curve y equal f of x at a specific point is equal to the gradient of the tangent to the curve at that point. So now we know that the gradient for any curve is the same as the gradient at a point. The gradient of the tangent at any particular point is the rate of change of y with respect to x. Also, the gradient formula for y f of x is given by the equation gradient equal f prime of x, where f prime of x is called the derived function. If we say f of x equal x to the power n, then the derivative of f of x equal to n multiplied by x to the power n minus 1. So you reduce the power by 1 and the original power multiplies by the expression. The gradient of a curve can also be represented by dy by d of x, where it represents the rate of change of y by the rate of change of x. So dy by dx is called the derivative of y with respect to x, and the process of finding dy by dx is called differentiation. When y equal f of x, dy by dx equal f prime of x. And then we continue. If y equal x to the power n, then dy by dx equal n multiplied by x to the power n minus 1 for all real values of n. It also can be shown that if y equal a power multiplied by x power n, where a is constant, then dy by dx equal n a multiplied by x to the power n minus 1. And again we reduce the power by 1 and the original power multiplies by the expression. If y equal f of x plus or minus g of x, if we have addition or subtraction, then dy by dx is equal to the derivative of the first term plus or minus the derivative of the second term. A second order derivative is written as d2y by dx squared, or f double prime of x, using function notation. You can find the rate of change of a function f at a particular point by using f prime of x and substituting in the value of x. So it's easy for us to do direct substitution. The equation of the tangent to the curve y equal f of x at the point a, where a is having the coordinates a, f of a is y minus f of a equal f prime of a multiplied by x minus a. And the equation of the normal to the curve y equal f of x at the point a is y minus f of a equal to minus 1 over f prime of a multiplied by x minus a, where the gradient for the tangent is different from the gradient of the normal. Normal is perpendicular to the tangent. So this is a summary for all or the most important points that we studied in this chapter, and it's important to keep it in mind.